Hello again. This is a video about standard potentials. So on the last video, we talked about voltaic cells or galvanic cells and how we could get energy from them and how we could set them up and how we use a cell diagram to define what they look like. In this video, we are going to talk about what's our standard potentials and how we use standard potentials to determine overall standard cell potentials when we combine those two half reactions together to get a cell. And then we're going to think about how can we use these standard cell potentials to find standard free energy changes and the value for equilibrium constants. So there's some review of equilibrium here. First, let's think about our cell potential. So we have a cell with an anode and a cathode, and part of the potential is due to the anode and part of the potential is due to the cathode. So how can we know the contribution of each half cell? Who is contributing what to the overall cell potential? And the answer to that is we need to compare everything to the same standard. We need a standard so that we can comparing everything to the same standard so we can figure out what part is due to the cathode and what part is due to the anode. If we have a standard, then we can use this equation where we have the standard cell potential is equal to the reduction potential at the cathode minus the reduction potential at the anode. Then we can look at the overall cell potential. If it's positive, then we know that delta G is negative and we'll have a spontaneous reaction. And if our cell potential is negative, then our free energy change will be positive and we won't have a spontaneous reaction and won't be able to get work from that system. So the standard most used is the power of Xi, the standard hydrogen electrode. In this electrode, we use the reduction of protons or hydronium ions to hydrogen gas. If we set this electrode equal to 0, right, so we've got the potential of this being 0, we can compare it then to everything else. So this is just a half reaction or a half cell potential. And so if we say that this one is 0 and we can compare everything to it, we will know what the electrode potential of all other half reactions are. So here's a picture of that going on. On this side, we have the anode side, we have the oxidation of zinc, and on the cathode side, we have the standard hydrogen electrode. So since we're setting this reduction to 0, and we can read the voltmeter of 0.76, that 0.76 is assigned then to the zinc oxidation. This can be used then to define all the standard potentials of all other electrodes, all known half reactions. And when we put them all together, we get what's called the electrochemical series. So this is just a small table from another textbook. There's a larger table in the back of your textbook in Appendix 6 that you'll be using for all the smart work problems and other activities and homework. So in this, what we have in the center right here, right, is our standard potential, right, our hydrogen electrode. So everything above it is going to have a positive potential and everything below it will have a negative reduction potential. So the more negative the potential, the standard potential of the half reaction, the greater the reducing strength of that half reaction. So that means it can reduce anything above it in the table if it's an order of potential. Here's where I want to ask, are there any questions? But no one's going to respond. I miss you guys. Okay. So we're going to think about how can we use this table then to figure out what's going on in a whole galvanic cell. How do we calculate the standard cell potential for a whole redox reaction? So here's an example where we're going to think about that electrochemical series and think about how we can use it. Which is the stronger oxidizing agent, copper 2 plus or silver plus in aqueous solutions under standard conditions? And then we're going to evaluate the standard potential of the appropriate cell, specify the cell with a cell diagram, we learned about those in the last video, and write the net ionic equation for the spontaneous reaction. So let's go back to our table for a second and think about, well, we've got copper, and where is silver? There's silver chloride. No, there's silver. So since silver is above it in the table, silver is going to be more strongly oxidizing because it has a more positive cell potential. So one way we can do this is say, since silver is more strongly oxidizing, then copper is going to be oxidized and silver is going to be reduced. So what I did is I took the reduction potential of copper 2 plus and I flipped it to make the oxidation. And when I flip that reaction, I have to flip the sign on the potential. And then I can simply add these up to get the overall reaction and the overall cell potential. Note that we're going to have to multiply this reaction by 2 so that my electrons cancel out. And also, when I multiply this half reaction by 2, I do not multiply the cell potential. Remember that cell potential is not dependent on how many multiples we have. So we can add this up. We get the overall reaction, copper being oxidized, silver being reduced, and we get a positive cell potential. So this is spontaneous, right? Because our overall cell potential, when I add these two up, gives me a positive number. If I flipped both of them, right, instead I re-oxidized the silver and reduced the copper 2 plus, I would get a negative 0.46 volts, and it would not be spontaneous. So we're also supposed to write a cell diagram. So keeping that in mind, oxidation at the anode, anode to cathode, we have the oxidation of copper solid to copper 2 plus, the reduction of silver plus ions to silver solid, and that's our cell diagram. Another way we can do that is to use that equation from the textbook that I also had at the beginning, where I have the overall cell potential is equal to the potential at the cathode minus the potential at the anode, which means I'm just taking the negative of the oxidation, the reduction potential to get the oxidation potential at the anode. So if I'm using this, I always want to use the reduction potential at the cathode minus the reduction potential at the anode. And of course, I get exactly the same value, a positive 0.46 volts for the overall reaction. So here's where I would usually say, it's your turn. You get to try this question out in class. So we've got cerium 4 plus and gold plus in aqueous solutions, and we want to do the same thing. Evaluate the standard potential of the appropriate cell, specify the cell with a diagram. We can assume a platinum electrode is used if no solid metal is involved in the half reaction, and write the net ionic equation for the spontaneous reaction. So I'm just going to click back through. So we are interested in cerium 4 plus, and that's the only one on our table right there, and gold. So you probably want to write these down, right? Gold reduction to gold metal is positive 0.169. Cerium 4 reduction to cerium plus 3 is a positive 1.61. There's a question. So now I want you to pause the video and try it. Seriously, pause the video and try this out and see if you can do it. Now that you're back, I'm going to show you what I did, and you can compare your answer. So since the cerium was lower in the table, we're going to flip that. It will be oxidized, and the gold will be reduced. Overall, we have one electron. So we've got cerium plus 3 plus a gold plus going to cerium plus 4 and gold solid. And the overall cell potential is the addition of these two. So negative 1.61 plus 1.69 are 0.08 volts overall. Our cell diagram would be, since we don't have a solid metal involved in this cerium reaction, we've got a platinum electrode, and cerium 3 plus and cerium 4 plus are in solution. Salt bridge to our gold plus, reducing to a gold metal. Alternatively, you can use this equation, the cathode minus the reduction potential at the anode, and of course you're going to get exactly the same answer, 0.08 volts. One of the really most useful applications of cell potentials is in the calculation or the determination of the standard Gibbs free energy of a reaction and also the equilibrium constant. How do we determine an equilibrium constant? So we used equilibrium constants to think about how much reactant and product are left after a reaction is finished once it reaches equilibrium. What we didn't talk about last semester is where do these equilibrium constants we look up come from? Now we get to talk about where those equilibrium constants come from, and they're really connected to the standard Gibbs free energy, and one easy way of getting at that is using cell potentials. So the reaction doesn't have to be a redox reaction for us to do this, as long as we can combine two reduction half reactions to get the overall reaction of interest. So even something as simple as the expansion of a gas. So for example, if we flip one reduction, which is making it the difference between the two, of hydrogen gas being reduced or being oxidized to hydrogen ions, we could think about that cell potential. And then we have the reduction of hydrogen ions to hydrogen gas at two different pressures, right? P1 and P2. If we add these together, we get simply the pressure change of hydrogen, right? Just the expansion of a gas from P2 to from P1 to P2. But that process can be related by just adding up the cell potentials or the potentials of the half reaction to get the overall cell potential. And here's how we can connect that to free energy. Right? So remember that the standard free energy is just equal to the negative of n, where n is the number of electrons being transferred, F is that Faraday constant of 9.6485 times 10 to the fourth coulombs per mole, and E sub cell is our standard cell potential. Free energy changes are also related to the equilibrium constant K via this equation, that the free energy change, the standard free energy change, is just equal to negative R, where R is the gas constant, 8.314 joules per mole Kelvin. T is the temperature in Kelvin, and K is the equilibrium constant. If we set these two equal to each other, we get a relationship directly between the equilibrium constant K and our cell potential, E cell naught. So let's take a minute to review equilibrium constants, just so that we can think through and remember that from last semester. Remembering that K, the equilibrium constant, is due to the law of mass action. At equilibrium, the composition of a reaction mixture can be expressed in terms of an equilibrium constant. So the general form for that equilibrium constant was activities of products over activities of reactants, those equilibrium activities raised to the stoichiometric coefficient. Some general rules to remind you of how that worked. Concentration is usually a molarity for all aqueous solutions. Pure liquids and solids are not appearing in the expression for K, and partial pressure of gases are used. Or if we think about this in terms of activities, which I like to think about it, so activities being what is changing in the reaction. For gases, as the reaction progresses, the partial pressure of the gas changes. So the activity is that partial pressure relative to the standard pressure of 1 bar or 1 atmosphere. And for solutions, for aqueous solutions, the activity is just that concentration relative to the concentration of 1 molar. And for pure solids and liquids that aren't changing, the activity is equal to 1. So in our expression for K, the activity is often just simplified as the concentration in terms of molarity or the value of the partial pressure in terms of bar or atmosphere. So what if we're not at equilibrium? How do we express what's going on when we're not at equilibrium? So you may recall there was a quotient, right? A general form for the reaction quotient looks really similar to the equilibrium constant. The only difference is for our Q, our quotient, the activities of products and reactants are not at equilibrium. So they could be, for example, at the beginning of a reaction or somewhere in the middle of a reaction where we could measure the concentrations. So for example, our cell, right? We could start off with a particular amount of concentration of ions in each half cell, and that would give us the activity. Where are we in the reaction? We can then connect this to free energy change. So remember, the standard free energy change, the one with the naught, is really just the pure difference between pure products at standard state and pure reactants at standard states. That's what our standard free energy change is all about. Our free energy change can be anywhere in the reaction, at the beginning, in the middle. Where are we in the progress of the reaction? So that depends on the quotient. How much is there? What are the activities of products and reactants at some place not at equilibrium? So we can find the value of the free energy change, whether it's negative or positive, will tell us if the reaction as it is spontaneous in the forward direction or the reverse direction. And that depends on the standard free energy change, that constant R, the temperature in Kelvin, times the natural log of the quotient. So let's put this all together with an example. So we want to calculate the equilibrium constant at 25 degrees for the following reaction. Silver chloride solid dissolving into silver ions and chloride ions. But wait a minute, isn't silver chloride supposed to be not soluble? And it turns out that it isn't very soluble, but it is sparingly soluble. So there's a whole class of compounds that we used to call soluble versus not soluble. In reality, there's some ions, right? This reaction still goes forward to reach an equilibrium. And we can use standard cell potentials to find the equilibrium constant for this reaction. Since it's a special class of reactions, solids dissolving into aqueous ions, they are called solubility product. It's still a K, it's still an equilibrium constant, but we put the little SP to tell us it's just a solid dissolving in water. So the expression, products over reactants, activities, concentration, since these are aqueous, 1 since this is a solid. So this is what our K expression would look like. Now let's think about how do we find what the value of K is, putting everything together. Our first step is to find two half reactions that when we combine them, we can get the reaction up here, the one we're interested in. The second step is to figure out how many electrons are transferred and find the standard cell potential when we add up those two reactions. So looking in the back of the book at I think it's Appendix 6, we find the following two reduction potentials, right? We have silver chloride solid being reduced to silver, metal, and chloride ions with a standard potential of 0.22 volts. And we've got silver ions being reduced to silver metal with a standard potential of 0.8 volts. So we want to look at these two reactions and think about how do we combine them to get the desired reaction. And it looks to me that if we just flip the second reaction, we'll get our overall desired reaction. Right? So instead, if we oxidize the silver metal into silver ions, flipping the sign, to negative 0.8 volts. And if we add these two reactions up, we get silver chloride goes to silver ions and chloride ions, and an overall cell potential of negative 0.58, which tells us that this is not spontaneous. But we kind of knew that already because silver chloride is not very soluble. Okay, we're out of room, so let's, and one more thing. We can also just use our reduction potential minus the reduction potential of the oxidation, and of course we get exactly the same thing of negative 0.58 volts. So we're out of room, so here's the same question. Our last step then is determine the value of the equilibrium constant K, or KSB in this specific example. So here's our reaction again. Overall, we find that silver chloride to silver ions and chloride ions has a standard cell potential of negative 0.58 volts. So we can use the equation we derived a few slides ago, that the natural log of K, our equilibrium constant, is equal to NFE cell over RT. If we combine all of these constants, right, R is a constant, F is a constant, T is temperature at 25 degrees C, we can simplify this equation to natural log of K is equal to NE cell over 0.025693 volts. This is a very handy relationship that you may want to write down, because it works for everything at 25 degrees. So then we simply note the number of electrons, 1 electron, 1 mole of electrons being transferred, negative 0.58 volts, divided by 0.025693 volts, we get the natural log of K is equal to negative 22.57. We exponentiate both sides to get the K. The value of K is 1.6 times 10 to the negative 10th. So the equilibrium constant is very small. Does mean it happens. There are some silver ions and chloride ions in solution when I put silver chloride solid in water, but not very many of them. Okay. So for some practice, you want to use the Appendix 6 to complete Activity 23. That is available on Sakai in our resources page as a blank activity, and also in the exams and activities portion where you're going to be able to enter in data. If you have questions at all, stop by for a meet, one of the opportunities for question Google Meets anytime. Bye.